Recording.
All right, so this is going to be our project, our end of the year project for feedback controls, the magnetic levitator. As you can see here, we begin with the structure, with a four-legged structure to basically keep our magnetic levitator still while it levitates the object. To begin, the attachment style we used to attach our solenoid to the actual base was through a metal rod in which I 3D printed a piece to hold an electronics and also just to slide into the black piece here that is epoxy, as you can see on the underside of the base. Inside of this basin is our solenoid used as the magnet. You might be wondering what this basin is for. It's actually because our solenoid itself gets too hot while we run it for longer periods of time. After the couple, maybe after 10, 20 seconds, it gets to the point where it melts and that causes issues. So I was tasked with basically creating a basin that would ensure that the solenoid would not melt and mess up the magnetic levitation process. So with that being said, I basically went out and bought some synthetic mineral oil, which is non-combustible and also not conductive or an insulator, which basically ensured that the solenoid could expend its external heat while also not creating any explosions or extreme heat of the oil itself in this basin. There was a basic MATLAB code ran to ensure that it basically dissipated this heat and it calculated the temperature of the oil over time to ensure about roughly how long we could keep it on before there would be any serious problems, which within the testing was with a fair amount of time. Additionally, these parts were created watertight via epoxy on the interior and the exterior parts of the actual solenoid itself, and it should work as a good base for our magnetic levitator.
I can talk about the levitator and how it was designed. So I started off with a 12 volt 8 amp source. It's 96 watts that it can output as my power supply, and I kind of just designed to maximizing this power supply at the time, not really knowing what we were going to do, just wanting to have the strongest magnet we could. And so then my job basically became what is our limiting factors for this coil, and pretty early on we decided that we were going to use a soft iron core, since we knew that had the highest magnetic permeability, which the higher the magnetic permeability, the greater mu r, which increases magnetic field, which magnetic force is equal to that squared. So the next thing, since we were using 8 amps as our unit, we knew we wanted a resistance to be somewhere around 1.5. So we knew how much wire we could use, and we knew how much or what material we wanted for the core. When we looked online, this was probably the largest core we could find, which is about a 1/2 inch in diameter. And so then I literally just ran a bunch of Desmos plots of equations relating the magnetic strength to resistance, length, right? And then I did one that related length and resistance or length and radius to magnetic strength. And what I found is about a 3/4 inch long core with a radius of 1/2 inch. So 1/2 to 3/4 is about 1.5 times length to radius, or sorry, it's a 3 times because it's a 1/2 inch diameter. So what I found was that was basically would saturate our core, which we found out that saturating the core would be our limiting factor. So it saturates about 2 torr, which is what this approximately outputs at the 8 amps. However, when we put this on for the first time, we realized that everything got way too hot way too quickly at the 8 amps, and just like generally sitting there, no matter what current it was at, it was just going to overheat. So heat dissipation became a huge part of the project. As you can see here, I can kind of demonstrate where the plug go. It is not plugged in. Cool. All right. so I can plug this in here and then plug in our magnet. Our object does stick to the bottom of it, right? And quite well. It takes a bit of force to get off. Like, that's quite difficult for me to remove. However, strength isn't everything. And we realized, like, it's already about melting the hot glue on it. And we realized it would melt the 3D print as well, which is where we first discovered it was just a bunch of smoke billowing out of it. So, if you want to talk about your sensor.
Just you can kind of record.
Okay.
So I'll talk about our sensor and its design. Our sensor is essentially two inductors, two coils, L1 and L2. L1 is excited by a 75 kilohertz sine wave signal, and what that does is it produces a magnetic field. And then when we have our object creates an induced voltage into L2. And so I'll just kind of show the sensor right there. You can see the output of the sensor. We have L1 and L2 as our inputs into our AD630 phase lock-in modulator circuit. Essentially, it multiplies both signals and then rectifies them, and also produces or provides a lot of filtering. We're using a fourth order Butterworth filter. And then we have the final output of that going to our capacitor, which is how we get our full DC signal. If there was no capacitor, we would just have a rectified sine wave changing in amplitude depending on the distance of our magnet. Ideally, we would want our output of this to go into our controller, and then our output of our controller to go into our coil driver, and then that to be hooked up to the magnet. But unfortunately, we could not get our coil driver working, and we kind of need to get our coil driver working in order to test values for our controller. So in order to get our controller working, we need our coil driver to be working, otherwise we can't test and get our coefficient values. So that's what we're going to work on in the next few days, and those are certainly future improvements to be made. This is our controller over here.
Yeah, it's a PD controller.
Yeah, it's a PD controller.
Do you want to explain why PD specifically?
Yeah, we went with a PD controller just because mainly a PD controller would work for this system. A P controller wouldn't be adequate enough, and a PID controller would not be necessary. It would work. A PID controller would work, but in very specific conditions. And so for this specific magnetic levitation system, a PD controller is the best choice.
Okay.
Yeah.